Okay, so this is the checklist from class, and I'm just going to go through and do all these videos, but then I'll do timestamps and link to them particularly. So we did this in class, that one. We also did this one in class, so I won't do a video, but so this is where we are now. So do page 2 of accumulation function packet together. Okay, so the accumulation function packet, this is the first page of it, and this is what we'll do together real quick. So page 2 of accumulation function packet. Okay, so here we are right here. Okay, so this will sound familiar, these questions, but first let's look. We've got this graph of m of x, and then h of x is an accumulation function that uses the graph of m of x. H of x gathers more area, underneath m of x, or accumulates it. And it's defined as the integral from -2 to any, any x value in the domain. Sorry. And then here we've got m of w. So they're asking, over which intervals is h increasing? Explain. And then at which values does h have local maximums or minimums? Explain. So it's asking about h. And so we've got h prime, h double prime. So we want to know when h is increasing. And this is the graph of m. Okay, so, but let's find h prime. Well, first of all, so we would know that h was increasing if we could see that h prime was positive. Nothing in particular about h double prime. And then at which values does h have local maximums or minimums? So just extrema. Maximums or minimums. Well, I guess we'll say both, like each individually. All right, so max, min. All right, so we're going to have a max on h if h prime has a sign change, positive to negative. And guys, all of these graph facts, really, you've got to visualize them. They need to make sense visually. They really do. If you just, keep trying to visualize it. So, and nothing about h double prime. So we've got to find h prime. That's what we need. So here's h. So I'm going to do d dx on both sides. So d dx on both sides. d dx of h of x is h prime of x. And this is equal to d dx of the integral from -2 to x m of w dw. Okay, and the thing about this, guys, if you are doing the derivative of an integral, as long as this variable is the same as this variable in the upper limit of the integral, that's what that's called. This is the upper limit of the integral, that's the lower limit of the integral. They're the endpoints of the interval. So as long as, this is just an x or y or something, and then down here it's the same variable. If that happens, then the derivative and the integral cancel each other, and then you could just cancel the dw because that was just for a dummy variable, or that was just part of the integral notation. And then, so what we're left with is just m of w. So we've got h prime of x is equal to m of, so w is a placeholder. And I actually want to address that in a moment. But w is just a placeholder, so it's a placeholder for what? For the whatever the variable was over here, which is x. So m of x. So guys, what we have, and when we do our explanations, we need to make this connection. What we have is that m of x, this graph, is actually h prime of x. So in our explanations, when we refer to this graph, we have to make clear that we know it's the derivative of h. So, and I've shown this work, and okay, but so I go over here. And okay, so increasing, so A. So I'm looking for positive. So this is H prime, the graph of H prime. I'm looking for where H prime is positive. So that is from 4 to 12. All right, so from 4 to 12. And guys, sometimes they will include the endpoints. I think it is a preference. Like there's sometimes when you definitely can't include them, and there's sometimes when you definitely have to, which I should address at some point, but sometimes it is a preference whether you include them or not. Okay, so it depends on like your explanation, I guess. So there's that. And then, or but we have to say why. So because m of x is equal to h prime of x, which means h of x is increasing, I'll say when m of x is positive. Okay, and now maximums and minimums. So B, okay, so a positive to negative sign change. So we've got sign changes at 4 and 12 on the derivative graph. Okay, sign changes there. This sign change, the derivative is going from negative to positive because this is the derivative graph. Okay, so the y values are going from negative to positive, and here from positive to negative. Okay, so we've got a max at 12 and a min at 4. Okay. Alrighty. Max at x equals 12 because m of x equals h prime of x. I don't have to say that. I don't know if I have to say that again, really. I think you could kind of just say it here. But they are presented as two different like questions. I don't know. Okay, so max at 12 because this, so h of x has a max when m of x has a sign change from positive to negative. Okay, and then similar explanation, guys, for the min, okay? So we would say min at x equals 4, and then I'll just say similar explanation. Alrighty, okay. So now, this next one. So this is about concavity. If you want to skip this, you can. Like if you think you get it, or you could like try to just do it yourself. But we're going to answer questions about concavity this time. So, oh shoot, we should. All right, yeah, I shouldn't have said that because I think you should. Well, you should at least try this. Okay, so anyway, all right, so concavity. So we've got to take the derivative, all right, of k. So over which intervals is k concave down, explain, and then at which values does k have points of inflection, explain. All right, this is k of x, and it is an accumulation function. And we're given the graph of q of x. Alrighty, so we'll take the derivative first, or you could set up the information first, but k prime of x is equal to d dx, the integral from 8 to x, dw. And you could do that move in your head, guys. You could go right to this. Oh, yeah, you could go right to k prime of x is equal to q of x if you could just, you know, visualize that middle move. Okay, so we're going to need to say that in our explanation. And they're asking us about k. So we've got k, k prime, k double prime. So first we want to know when k is concave down. And then they're asking about points of inflection. So K is going to be concave down if K prime is decreasing, which would mean K double prime would be negative. But the graph we're looking at is right here. All right, that's Q of X is right there. So we're going to be looking at this graph for where it is decreasing. Now, point of inflection, how are you going to see that on the K prime graph? You're going to see an extrema. So a max or a min. If you had K double prime, you'd be looking for a sign change. Okay, alrighty, so if I look up here, all right, so for A, for concave down, I'm looking for when this Q of X is decreasing. So from 9 to 14, but then again from 17 on. So from 9 to 14. Okay. Okay, I'm just, sorry. So here's this, and then the reason. Since equals Q of X, K of X is concave down when Q of X is decreasing. Okay. Yeah, so guys, usually you wouldn't have like back-to-back questions like this, so you wouldn't have to keep saying that over and over. I think to be careful, I probably should. You know, these are just exercises. Yeah, okay. So, yeah, I'll keep repeating that. It's worth repeating. So B, at which values does K have points of inflection? And so now we're looking for extrema. So there's an extrema at 9 and 14 and 17. X equals 9, 14, and 17. Since K prime of X is equal to Q of X, K of X has points of inflection. Oh, sorry, you can't see. Points of inflection when Q of X has extrema. Technically local extrema, but you could just say extrema. It's implied. Okay, so there is that. And, okay, so moving on. All right, so we just did that. Okay, so moving on to this, we're going to do the problem on page 1 of the accumulation function packet together. Okay, so that is this one. And alrighty, so f prime of x is equal to this. And we are given that f of 1 equals 3. This is what they call an initial value. And if you have an initial value, that's great because it could help you go backwards to a specific antiderivative value if you have the derivative. So first they're asking find f double prime of x without a calculator. Okay, so this is f of x. So maybe, guys, what you should ask yourself first, so is it a one-step? No. And then when I first was teaching this, I would say to think about product and quotient next, which is true, but I think we could identify, right away if you're going to need a U substitution. So if you know you're going to need one, do that maybe. Like you could do it right away. I'll do it now so you could see what that would go like. But so this is f prime. So I could see right now that U is going to have to be 5x at some point. Okay, and then whenever you find a U in calculus, you go du, dx. Okay, and then from here, what I've got is f prime of x is equal to 2x e to the u. Okay, and then maybe from there you could do set up the product rule because we have not taken the derivative yet. So now I'm doing d dx on both sides. So d dx of f prime is f double prime of x. And then d dx on this side, but I need product rule. All right, and I won't mess it up this time. So d dx 2x e to the u comes down, plus 2x comes down, d dx e to the u. Okay, so we've got f double prime of x is equal to, so the derivative of that is just 2. So 2 e to the u plus 2x, okay? Now the derivative of this, all right, so the normal derivative, if the variable were u, the derivative is e to the u. But since the variable is not u, by chain rule, you need du dx. Okay. And okay, so that's this whole part. So plus 2x, and then this comes down, e to the u, and then du dx you already found, like off to the side. So times 5. So f double prime of x is 2 e to the 5x plus 10x e to the 5x. Okay. Oh, and guys, just by the way, you could factor this if you wanted. But you don't have to, but just in case, I just want to point out you could take out a 2e to the 5x. And that'd be 1 plus 5x. Excuse me, like if you had to, set this equal to 0 or something, that's what you would want to do. Okay, so that was find f double prime of x without a calculator. Now we're going to find f of 2. So here's the situation that we're in. We've got a derivative sequence. Okay, and we're starting in the middle. Okay, and we just found the derivative, or instantaneous rate of change, to get f double prime. But now we need to go backwards. So to go backwards, you're going to need to do the antiderivative because you're going to need to use the net change theorem. Net change theorem to go backwards. And they gave us the initial value. So the initial value is equal to f of 1, which is equal to 3. Okay, so that's the initial value. So, okay, so f of 2, net change theorem, so f of 2 is equal to f of 1, final value equals initial value, plus the integral initial time to final time, and then dx, f prime of x, but this is 2x e to the 5x. Okay. All right, there we go. This is 3. So this is equal to 3 plus the integral from 1 to 2, 2x e to the 5x dx. Okay. And then you ask yourself, you're like, oh, okay. So is it necessary to use Math 9? Okay, so this is a very important question. Or it's important to know when you have to. So, basically, for our purposes, we don't go past U substitution and maybe some algebra, before doing it. But there are other methods, but we don't go past that. So, if you can't make U substitution work, then you have to use Math 9, okay, or something else, which I'll talk about. But so anyway, let's go through it. So what would U be? Or if it did work, what would it be? So try u sub. So u would have to be 5x. Du dx is 5. So dx is du over 5. So just imagine, try to think forward. If I put over here du over 5, that is going to leave us inside here with 2x e to the u, and this x is not going to cancel. You are not going to be able to get the x's to cancel, so won't work. Won't work. Yeah, so won't work, so we would need math 9. Need math 9. So, let me get my calculator. Okay, so 3 plus math 9, 1 to 2, 2x e to the 5x dx. Okay, cool. 15814.563. Okay, guys, there it is.